Uh, so yeah, so the plan of this talk is to cover the following things. So I will explain what symplectic topology is about. I think this window is really disturbing. Okay. Give me a minute, please. Yeah. So I would explain what symplectic topology study, and then I will explain you an invariant called Lagrangian capacity, and then I will explain some problems related to the Lagrangian capacity and the progress we have made so far. Okay. So let's start with the definition of symplectic vector space. A symplectic vector space is a vector space with a bilinear two form omega, which is non-degenerate and skew symmetric. The non-degeneracy here means the following. So if you flag a vector in one component, you get a linear map from V to R. So this way you can define a map from V to its dual by sending a vector to its omega dual. And non-degeneracy means that this map is an isomorphism. Okay. And a symplectic manifold is a smooth manifold M together with a choice of differential two form such that the following hold. Each tangent vector space is a symplectic vector space with respect to omega p. And there is this technical condition that the Durham derivative vanishes. Okay. This is basically motivated by Hamiltonian dynamics. I will explain later. So basically, a symplectic manifold is just a smooth manifold where you put a symplectic vector space structure on each tangent space. Okay. If you take a closed manifold, then the question whether it admits a symplectic structure or not. So it's not always the case. For example, if you take so if you take a symplectic manifold, then since the omega is closed by Stokes theorem, it can't be exact. Otherwise, it would give zero volume. So it gives you a non-trivial element in the second de Rham cohomology of M. And if you take the wedge product, then you get a four form, which is also giving you a non-trivial element in the de Rham cohomology groups. And so if you take a manifold which has vanishing de Rham cohomology groups in even degrees, then that manifold cannot admit a symplectic structure. And it's also a simple exercise that every symplectic manifold has even dimension. So odd dimensional manifold do not admit symplectic structures. And it is believed that the sufficient condition and necessary and sufficient condition for having a symplectic form and a closed manifold is that it should admit something called almost complex structure, and the even dimensional de Rham cohomology groups should not vanish, and there should be enough to have a symplectic form on the manifold. And I'm not sure if it has been settled. It still seems to be an open problem in higher dimensions. Okay. So let's take some examples. So Q1, P1 to Qn to Pn, these are the linear standard coordinates, and you define the two form by just taking the wedge product of the differential of these individuals one forms. And if you identify the R to the N with C by sending these past two components to this complex number Q1 plus iota P1 and so on, then you get this was symplectic structure I wrote down here can be written in this form. Okay. And other examples, of course, you can just take any open subset of the Euclidean space and then the restriction of the standard symplectic form will give you a symplectic structure. There are other nice subsets of Cn that are very important in symplectic topology, and they're called toric domains. So I'm going to define them now. Take a domain in the positive part of Rn. So these are basically vectors whose all components are non-negative. So you can just imagine something like this. I have shown in dimension 2 where n is equal to 2. And you can define a map. So consider this map, which basically sending a vector to the lengths, the corresponding lengths of the components like this, and you scale by pi. Pi is just a rational number, 3.14, something like this. A toric domain is a subset of Cn which can be written as an inverse image of some domain like this. Okay. And a toric domain is convex if you reflect this subset along these x-axis and along the diagonal line, then you get some region which I denote by omega hat. If that region is convex, then we say the corresponding toric domain is a convex toric domain. And there's a number we assign to toric domains. It's basically the supremum were positive numbers A such that this diagonal vector can be placed inside this omega region. So in the picture, this number is something proportional to this line that you see. Okay. Of course, I don't assume that this line can be placed in omega. It's just the vector, the tip of the vector that can be placed on omega. Okay. So in particular, if I take omega to be a triangle with one side equal to A1 and the other side equal to A2, then the corresponding toric domain is gonna be this ellipsoid I have written down. And if you take both these sides to have equal length, then you are getting the round ball of radius A divided by pi square root. Okay. And explicitly, you can you can compute the diagonal, and it's gonna be for the ellipsoid, it's gonna be this number, and for the ball, when you put both of these to be equal, you're gonna get this number A divided by 2. In higher dimensions, if you take an n simplex instead of a triangle, you're gonna get this n-dimensional ellipsoid, which basically you parameterized by these n real number that corresponds to the vertices of the simplex. And you can play the same game to compute the diagonal, and it's gonna be this number. And if you plug all these values to be equal, then you're gonna get the round ball, and that has diagonal A divided by n. So if you take a convex toric domain, then you restrict the symplectic structure from the Euclidean space. This gives you a symplectic manifold with boundary. If the boundary might have some singularities, but that's okay. Here's an example of non-convex toric domain. So you take some positive number delta, and you look to these two strips, the vertical strip up with delta and also the horizontal strip, infinite strip up with delta, and you take the union. And if you take the inverse image of this under this standard moment map, the toric domain you get is something we call non-disjoint union of cylinders. And it's basically disk times C. So it's a cylinder and also C time a disk. Okay. And they intersect along this key, basically. And it's not convex, of course, because this image is not convex. Okay. So next, I'm gonna give you some motivations for symplectic topology. So consider in masses M1 to N, and you have placed them, let's say, at locations from X1 to Xn in R3. So it's like N masses placed at different location in space R3. And the question we asked that if we give them initial velocities V1 to En, then what happens to this system of masses? This is the classical n-body problem. There are different formulation of this problem, and I will discuss only one here. Consider a vector where Q1 represents the position of M1 in time t, and P1 the momentum of M1 after time t. And you continue, so you make this big vector, which I call the state vector of the system. And since you have you have like three components for the position and three components for the momentum. So each particle has six-dimensional space. So it's like a vector in R to 6n. And we know that this vector satisfies this Hamilton's equation, which is basically first order system of equations, where the vector field is written as corresponding to the total energy of the system, given like this, where V here is the potential, the Newtonian potential. Okay. And of course, if you want to determine what happens to the system, one's asked to solve this system of equations. In the n-body problem, we are basically interested in periodic orbits. So basically, we ask what are the initial conditions that leads to periodic orbit. So the orbit basically repeats itself. Recall that this space or of the system, which is this Euclidean space, it admits this standard symplectic structure I explained above, which is given like this. And you can observe that the vector field, the Hamiltonian vector field in these equations, is the unique vector field satisfying this equation. So what is it? So if I take the differential of this function h, it gives me a one form on the Euclidean space. And as I explained that the symplectic form is non-degenerate, so for each, there is a one-one correspondence between the one forms and the vector fields. So dh, the differential of h, gives you one form in the Euclidean space, and therefore you can find a vector field that is dual to omega, dual to this. And that vector field is basically the vector field that appears in the Hamilton's equations. So what does it mean? It means that the symplectic structure of the Euclidean space basically encodes the laws of motions. And the second thing it says is uh, if you want to write down Hamilton's equation, you do not need global coordinates to write them down. In this case, you need, of course, these global coordinates, but if you consider an abstract manifold and you want to talk about Hamiltonian equations, then you would somehow need global coordinates, which you usually don't have it. So the structure you need to write down Hamiltonian equation is basically the symplectic structure, a symplectic structure. So therefore, it can it motivates the following. If I take a symplectic manifold and I take a Hamiltonian function or just a smooth function, which is basically time dependent, you can take it to be independent. Then there is a vector field determined by this, and it's basically the unique vector field um, given by this equation. So if you fix this time parameter, then you get a smooth map on M, a smooth real valued map on M, and the differential is a one form, and for that you find a dual vector field. So for each t you can do this, and therefore you get a time dependent vector field, which I call Hamiltonian vector field associated with the Hamiltonian H. Now, as I explained that the symplectic structure how encodes the laws of motions, and it's natural to ask what is basically the connection between the dynamics of a Hamiltonian system and the topology of the manifold. And so there is a good link between the two, and it says the following. If you take a compact symplectic manifold and then there is a open dense subset in C infinity functions such that for any function you count orbits, one periodic orbits, and that's at least some of the Betti numbers of the manifold. It's basically gamma is a loop from the circle, unit circle, which satisfies this Hamilton equations corresponding to H. And this hash is basically a set theoretic count of this. One can prove that for generic H is going to be a finite number. And so the set theoretic count of this one periodic orbits is at least the sum of the Betti numbers. Now, this is a very important theorem in the following sense. So this side is something coming from the topology of the manifold. It has nothing to do with the dynamics. But this side is totally coming from the dynamics. And the theorem is somehow connecting the two, that one is basically abstracted by the others. Okay? And so one might, in this case, you don't see the symplectic structure much. It's just pure topological invariant you see. But one can ask what is basically the correct, or what is the connection between the symplectic topology of the manifold and the dynamics. And one can expect that because if you take loops, the space of loops, smooth loops on M, which are contractible, then you can define the action by taking a loop and take a smooth disk with boundary there loop and integrate the symplectic structure via the fullback of their choice, minus integrating the Hamiltonian over the orbit. And one can compute to show that the critical points of this function, which are basically one periodic loops, you can say, are precisely the periodic orbits of the corresponding Hamiltonian system. And so the about theorem is basically telling that the critical points are at least the sum of the Betti numbers, and it's something you have seen in Morse theory for smooth functions, that some of the critical points of a smooth function, a Morse function, is at least the Betti number, but this one is counting periodic orbits. Well, the functional basically, if you look, is determined by two things. The first part, which is the integral over the symplectrum, it's coming from the symplectic topology of the manifold. And the second one is coming from the Hamiltonian, the dynamical part. And so the critical point of this function, which are periodic orbits of the system, are determined by both the system itself and also the symplectic structure of the manifold. And therefore, you can expect that there's going to be an interesting link between the symplectic structure and the dynamics. And so one can ask the following questions. If you understand a Hamiltonian system and a symplectic manifold, what does it mean for the topology of the manifold? And if you understand the topology, well, what does it mean for the dynamics of a Hamiltonian system? And this was the initial motivation for symplectic topology, but now methods from symplectic topology could be applied to Riemannian geometry and spectral geometry and other kind of related areas. For example, in Riemannian geometry, there is this problem of finding minimal submanifolds, and minimal submanifolds in Keller-Einstein manifold are basically monotone. So there's some kind of connections happening between symplectic topology and other branches of maths. Okay, so it's enough for motivation. And so next, if you want to study a manifold, it's basically you are looking to, one way to do is to look to submanifolds of the given manifold. For example, in Riemannian geometry, you would probably like to look for one-dimensional like closed geodesics, which are basically one-dimensional submanifold, and maybe minimal manifolds, and so on. So in symplectic topology, we have two types of special submanifolds. One is symplectic submanifold, which basically there are many submanifolds such that the symplectic form restricts to a symplectic form on the submanifold. And there's another type where the restriction of the symplectic form completely vanishes. And so I would talk about the ones on which the symplectic form vanishes. And they are called isotropic submanifold. Okay. So a submanifold L of a symplectic manifold M is isotropic if you restrict the symplectic form to the tangent space of the submanifold, then it identically vanishes for every point. Okay. There is some linear algebra. One can prove that every isotropic submanifold of a symplectic manifold has dimension at most half of the dimension of the manifold. And as I mentioned, that symplectic manifold have even dimension, so this is basically half of the dimension of the manifold. And of course, you can take the extreme case where the manifold has dimension half of the total dimension. And this leads to the following example, a following definition. Consider a symplectic manifold and a submanifold L. We call it Lagrangian if it is isotropic. So the symplectic form has to vanish identically, and the dimension of L is half of the dimension of the manifold. Okay. So let me give you some example of Lagrangians because I'm gonna talk about Lagrangian submanifold for the rest of the talk. If you take a symplectic plane R2 with this standard symplectic structure, and you take any curve, smooth curve, like one-dimensional submanifold, gamma, then the tangent space is basically one-dimensional. So if you plug the same vector or its scalar multiple, then the skew symmetry of the symplectic form tells you that it has to vanish. So one-dimensional submanifolds are Lagrangian. And of course, you can take a circle that would be a Lagrangian torus, one-dimensional torus. Okay, and you can build upon it, and you take a circle of radius R1, take the product, take in circle, and then take the product. So it's gonna be a submanifold of R to N. And since the symplectic form is basically the sum of the individual symplectic form on each plane, therefore each circle is Lagrangian, and therefore you take the product, so that's gonna give you a Lagrangian torus. Okay. Now there is a theorem which I would just state it as a remark because I'm not very precise in its statement. It says that if you take a smooth submanifold, just a smooth manifold, and its dimension is strictly less than half of the dimension of the symplectic manifold M, then any smooth embedding of L, you can smoothly deform it to an isotropic embedding. Of course, there is some homological assumptions one should make here, but what I want to say is that the only abstraction that comes to you to deform a smooth embedding to isotropic and is based purely topological. There is no symplectic abstraction to you. Okay. And this is something called H principle for subcritical isotropic embeddings. Now, this is basically not the
Sorry,
case.
so it is strictly less than the half of the dimension, or less or equal?
Strictly less than half of the dimension.
Yeah, so in the remark it is less or equal. No?
I mean, you're gonna get even dimensions for L anyway.
Ah, yes, yes, exactly.
So,
Sorry, sorry.
no problem. Yeah, and but this is not the case when you take Lagrange L to be Lagrangian. So you can find embeddings, but you can't deform them. So there are some like abstraction coming from the symplectic structure of the manifold. Yeah. And I can mention one example. So if you take R4 with the standard symplectic structure, then the only oriented closed surface that you can embed Lagrangianly is the torus. You cannot do it for sphere or any other surface. But you can build um, isotropic embeddings, okay? Subcritical isotropic embeddings. So it's basically, so what I want to say through these two statements is the following. Among the isotropic submanifolds, Lagrangians are basically the submanifolds that interact with the topology of the ambient symplectic manifold. Because the others are like this pure topological, they don't care much about the ambient structure. But Lagrangians are very much sensitive to the structure of the ambient symplectic manifold. So they interact with the topology of the symplectic manifold. Okay. And among the Lagrangians, there is another class of Lagrangians that interact the most with the symplectic topology of the ambient symplectic manifold. They are called monotone, and there's a generalized version of it called extremal. And so in this talk, I'm gonna define invariants for symplectic manifolds based on Lagrangian submanifold. Okay, and that invariant is called capacity, symplectic capacity. Let me give you a definition for that first. So take a class of symplectic manifold, all of which have the same dimension. And then a symplectic capacity on that class is just a function to the positive, the non-negative reals, such that to each symplectic manifold, it assigns some number, but that number is behaving like area. So you scale the symplectic form by some positive constant, the whole number is scaled by that number. And if you take a symplectic embedding of one manifold to the other of the same dimension, then you have this monotonicity behavior of this function. So it's basically give you abstraction when you can embed one symplectic manifold to other. And in particular, if there is a symplectomorphism between two manifolds, a symplectomorphism is a diffeomorphism that full spec the symplectic structure of one to the other. So if you have a symplectomorphism, then this tells you that this number has to be equal for both. So it's a symplectic invariant. And the third one is that it's not something trivial. So for the round ball in the standard Euclidean space, it has to be positive, and for the cylinder, it has to be finite. So basically, you are saying that it should not be like volume. So volume is, by example, infinite for the cylinder. Okay. So these kind of functions are called symplectic capacities. Okay, so I'm gonna define one using Lagrangian submanifolds. So let's define the symplectic area first. So take a symplectic manifold M and a Lagrangian submanifold L, and you can define a number which is basically you look to smooth disk in your manifold with boundary and the Lagrangian in the picture I have shown. But you look to only those smooth disks which has positive symplectic area. So the integral of the symplectic form is positive. And then you take the infimum over the symplectic area of these smooth disks, positive symplectic area of these smooth disks. So you're gonna get some number between 0 to infinity. I mean, of course, if there is no such disk, you are gonna get plus infinity. And this number is called the symplectic area of L. You can take the example for the torus I wrote down. So the symplectic form is exact. So if you integrate any disk, then that integral is equal to the integral of the one form or the boundary of the disk, and is gonna give you this integral combination of the areas of these circles. And if you take this torus such that each circle has same area, then you get this pi r square. Okay, so what does this symplectic area measure? Okay, so there's a conjecture by Chilibak-Monkey, and it says that if you take a Lagrangian torus in the standard Euclidean space, and you try to enclose it in some round ball, then if you take a ball of size n times the symplectic area of the Lagrangian, then you can't enclose it in that ball. So if it hits the interior of the ball, it's gonna go out of the ball. For example, this picture is not possible. This is not possible. This is possible, and the Lagrangian can be completely on the boundary that's possible. So this basically tells you that if the symplectic area of the Lagrangian torus L is very big, then you need a very large ball to enclose that Lagrangian. And not only that, like this kind of behavior is not possible. So it's basically, it also tells you how the Lagrangian sits in the ball. So somehow it remembers the extrinsic geometry of the Lagrangian. Okay. The Lagrangian capacity is basically the maximal symplectic area of a torus sitting in M. So basically you take a Lagrangian torus, take the symplectic area, and then take supremum with respect to Lagrangian tori, and this be some number. This is a capacity. Well, there is some extra conditions to make it capacity, but yeah. So this and the Lagrangian torus is called extremal if the symplectic equals is maximal. So that's basically equal to the Lagrangian capacity. Okay. So here's an example which I should skip. The Lagrangian capacity of CPN, Chiribak-Mange computed it, and it's equal to this number 1 over n plus 1. Per the standard unit ball, it's 1 over n, and per the cylinder, it's 1. There are three conjectures Chiribak-Mange stated in the paper they wrote. It says that every extremal Lagrangian torus in the ball is contained entirely in the boundary, so it cannot hit the interior. And the Lagrangian capacity of the ellipsoid, the n-dimensional ellipsoid, two n-dimensional ellipsoid I wrote down above, is exactly equal to the diagonal of the ellipsoid. And there is a third conjecture which says that extremal tori are basically a replacement for monotone tori. So in CPN, monotone tori are the same as extremal tori. So here's a progress on this conjecture. Georges Dimitroglou Ritzel actually proved the first conjecture for dimension 4 in dimension 4, and it says that every extremal torus in the 4-dimensional ball lies in the boundary, and he also proves that there is a unique such torus up to Hamiltonian isotopy. Okay. Michael Pereira, who was a PhD student of Chiribak, he proved the second conjecture, saying that for 4-dimensional, sorry, it has to be 4. So 4-dimensional ellipsoids, the conjecture holds that the Lagrangian capacity equals the diagonal of the ellipsoid, and if the linear contact homology of the ellipsoid is well defined, then the conjecture is true in all dimensions. Pretty proved. And different people, including me, proved that in CP2, the third conjecture is true, which means that Lagrangian torus in CP2 is extremal if and only if it is monotone. In my PhD thesis, I managed to prove the first conjecture in all dimensions. So for every n, every extremal Lagrangian torus in the twin-dimensional ball is entirely contained in the boundary. There are a few observations based on this statement. So it's implies that extremal tori and the ball are in 1-1 correspondence with the Hamiltonian isotopic classes extremal tori in CPN -1. And basically, there's 1-1 correspondence between Hamiltonian isotopic classes of extremal tori and the 6-dimensional ball and Hamiltonian isotopic classes in CP2. And for n greater or equal to 3, there are infinitely many Hamiltonian isotopic classes of extremal tori in the ball of dimension 2n. And there basically one can build them by lifting monotone Viana tori from CPN. Okay. So question one can ask is, of course, the conjecture is true for ball, which are basically very round in geometry. What about other toric domains in CN? Is it true that every extremal torus in a given toric domain is entirely contained in the boundary? I made some progress on this one, and for the cylinders, if you take a round ball and times Cm for any integer m, then the Lagrangian capacity doesn't change. It's the same as the ball. And every extremal Lagrangian torus in this cylinder is entirely contained in the boundary of the cylinder. For 4-dimensional, there's a larger class of toric domain for which this is true, and these are basically toric domains that you can enclose in a 4-dimensional ellipsoid of the same diagonal. For example, in this picture, this green side is basically the boundary of the ellipsoid. So this triangle is representing the ellipsoid, and the toric domain corresponds to omega in the blue, and it's inside the ellipsoid, and it has the same dimension. It has the same diagonal as the ellipsoid. And so if you have such a toric domain, then every extremal Lagrangian torus in that domain is contained in the boundary intersected with the boundary of the ellipsoid. So somewhere here or somewhere here in the picture. So the theorem basically prove that in ellipsoid in particular, extremal tori lies on the boundary, and they always intersect this. Is going to be next theorem. So basically, this theorem covers all ellipsoids in particular. Yes. Yeah. And well, so an extremal torus is either here by the above theorem or here. So where is it? So the next theorem is basically saying that it's in the connected component of the intersection of the boundaries where this product torus is lying, which is this black dot. So every extremal Lagrangian torus in that domain intersect this point, which is corresponding to the product torus I have written down. Okay, so there is no extremal torus here. It's always near the diagonal of the domain. And in particular, if you take an extremal Lagrangian torus in the ellipsoid, you cannot displace it by Hamiltonian isotopy. By displacement, I mean that you cannot find a family of symplectic maps that can take the Lagrangian away from itself completely to make it disjoint. Okay. So these basically are the cases where the conjecture is true. The conjecture is not true if you take a non-convex domain in general. So here is an example. I take a non-disjoint union of cylinders of width 1/2. So delta I have fixed to be 1/2. So it's something corresponding to the union of these two strips, these infinite strips. And I consider three-dimensional unit sphere, which I see it as a half vibration over CP1. So P is the projection in the half vibration. So it's S1 bundle over CP1. Okay. And S3 in this toric image corresponds to this red line, which is basically the boundary of this triangle corresponding to the unit ball. So it's the boundary of the unit ball. And so if I take a embedded closed loop on CP1 and I lift it, take the inverse image P, then that gives me an embedded torus in S3. So it's a Lagrangian torus in S3. Well, it's a Lagrangian torus in the unit ball, which is contained in the boundary, which is S3. But I take the loop such that it bounds an area equal to half of the total area. So let's say CP1 has area 1. And if you remove that loop, it split the sphere into two disks. And each disk has area 1 or 2. That's what I mean. This. So now if you take this kind of loop, you lift it, you get a Lagrangian torus. And that torus is basically extremal in this non-disjoint union of cylinders. Now here, if I take L to be the equator, then it just lifts to this black point, black dot. But if I take this loop to be something different from the equator, then it's gonna be something that intersect, because there's a theorem that any loop that bounds half of the total area has to intersect the equator. So if you lift it, there's gonna be some torus which would intersect this black dot. So this black line is representing the lift of L. Okay. Now this is an extremal torus, but it hits the interior of this toric domain. So it's not completely on the boundary of this non-disjoint union, which is corresponding to this. And so the conjecture that every extremal Lagrangian torus and non-convex toric domain lies on the boundary is not true. And this is a counterexample. Okay, I think I should stop here. Thank you very much for listening.